All right, ladies and gentlemen, hello and welcome back once again to the only coast to coast radio show all about the information economy. It's time for Inside Analysis. Yours truly, Eric Kavanagh, is here. And folks, today we're going to go deep, deep down to the molecular level, folks. We're going to talk about quantum computing and we're going to talk about atoms, like using neutral atoms. Are you kidding me? We've got Nathan Gemelke. He is the CTO and co founder of a company called QuEra Computing. That's QuEra Computing, and they have some interesting announcements. They're doing quantum computing. Nathan, welcome to the show. Well, how you doing today?
Thanks, Erica. Really great to be here. Love to share what we're doing at QueRa today.
Yeah, so quantum computing, we've talked about this for years now, and IBM is doing some interesting things. There are different ways you can achieve quantum computing. I think that's one of the key considerations here. But it is fundamentally different than traditional linear programming, if you will. Can you kind of start us off giving us that high-level description of what makes quantum different at a fundamental sort of first principles level?
Yeah. So, I think most people are probably familiar with the idea of computing and representing information using bits.
Hmm.
In a classical computer, we use a classical bit. And so a bit is basically just a switch. It's an on or off state. And so, nowadays we make those out of not just, the kinds of things that we started with way back, 100 years ago with actual mechanical switches, but we invented these electronic switches called transistors. And now we've got billions of these things on a chip. And they're really efficient, they're really fast at what they do, and we built an entire industry of information processing around those classical bits. Quantum computers are different at the bit level. We do is we reintroduce a new kind of bit. We call it a quantum bit or a qubit. And a qubit is really fundamentally different from that classical bit in that it obeys the laws of quantum mechanics. And so one of the unique things about quantum bodies, usually these are microscopic things like single atoms or single photons, things like that. But we can put them into states that we can actually superpose, which is to say that we can put them in the on and the off state simultaneously. That's called superposition. And
Hmm.
we've known about that idea in quantum mechanics for about 100 years. Now we're starting to get the technology that can get a hold of these quantum bodies and do that in a highly controlled way. And if we have lots of bits, at least two, we can start to do one of the other unique features of quantum mechanics, which is start to use entanglement, which is really starting to correlate the states of multiple qubits. And
Hmm.
the real power of a quantum computer comes from it's the information representation power of large ensembles of these quantum bits that we can put together allows us to store exponentially more information than we could in a classical computer.
Yeah, I mean, this is really fascinating stuff. And like you say, we now have the power to hold them in place, and you're using lasers to do that. Is that right?
Yeah. So one of the joys of my job is that I get to make actual things, so it sounds like science fiction, but you get in the laboratory and it's an actual thing. So, we're definitely in the research and development phase, but the way that we make our quantum bits is we actually use single atoms that are in a very dilute vapor inside a vacuum chamber, and these are really good vacuums. So there's almost nothing there except for the few atoms that we want to use. And what we do is we use laser cooling, which is the technique of using same kind of lasers that you find in laser pointers to cool the atoms down to microkelvin temperatures. So that's a millionth of a degree Celsius above absolute zero. We do that trick all with lasers. So there's no, big cryogenic system like you might see for these.
Yeah, right. That was the stories. You had to use cryogenics, and now you don't, right?
Yeah. So actually with the neutral atoms, we don't have to do any of that. And the machines are much simpler, much cheaper because of that. And starting from that point of getting the atoms super cold, we can grab them one by one by just using focused laser beams that we call optical tweezers, and basically pick up those atoms in that vapor cell one by one, move them around where we want to, and then we use other laser beams to excite the electronic states of the atoms to represent that on and off state of the quantum bit.
That's so amazing that you can actually manipulate atoms, individual atoms at that level. And so when you're actually persisting data, let's say in a quantum space, what you're doing is what you're just kind of holding them in this position and waiting for some instruction that come and reads it somehow. Like, how does it read?
Yeah, no, exactly. So all the information processing in a quantum computer based on neutral atoms is really done by using controlled pulses of laser light. So we're actually, focusing laser lights down onto each of these single atoms one by one. In time, we're flipping the state of the atom, exciting the electrons inside the atom using these laser pulses. But the key for quantum information, and this is something that is really very difficult to do, and it's why it's taken so long to be able to get to this point, is to preserve that quantum information. So the big bug
Hmm.
about quantum computing is called decoherence. If your
Mm.
system decoheres and it loses its quantum information too quickly, if you can't keep up with that decoherence process, you'll end up with basically just a very expensive classical computer if you can't stop that from happening. So there's two
Hmm.
ways to do that. One is just to have a very, very good qubit. Neutral atoms are very good qubits, and evidence of that is actually, if you look at your wristwatch right now, you can trace back the time that it's keeping back to an atomic clock that's run by the National Institute of Standards here in the US. And that atomic clock is actually run off of transitions as neutral atoms. So they're very
Hmm.
good qubits. For the same reason that they're good as clocks, they're good as qubits. But the other way that we have to fight against this decoherence mechanism is to use something called error correction. And so error correction is something that you can also do in classical computing. And in fact, it's a key step inside the CPU inside your laptop today. But in quantum computing, being able to fight against that decoherence mechanism by using methods of error correction, which is basically representing a single qubit with multiple qubits that kind of encode the state in a robust way. If you can do that, that's a key step along the way to making scalable quantum processors. And we basically just passed this important step of being able to do error correction just within the last year or so.
Wow. That's very, very interesting. Now, one of the challenges, of course, is that you need to design a whole system around this in order to be able to leverage this stuff. So what have you built leading up to now to enable your innovations that are happening today? What's the rest of the sort of system itself that runs these atoms and manipulates them?
Yeah, so I mean, if you come in, you walk into one of our systems today, I literally mean you can walk into it. Okay, so
Wow.
this is like going back to the days of ENIAC, with electronic computers.
Right.
You walk into QuEra's labs right now, you'll see a machine that, looks an awful lot like, a bunch of lasers and optics sitting on a table, and you would not recognize it as a computer. And honestly, it's a research and development job right now to make these systems in the first place. But they are thousands of pounds of equipment, a lot of laser light bouncing off of a lot of complicated optics setups. But that's the state of the art right now. Over time, we'll work to make these more of a commodity, get them into a product form that they can be placed in remote places.
Hmm.
Excited. We're a 6-year-old company. We put our first system that we built this way up online on AWS Brockhet. It's a service that provides cloud access to quantum computers to basically anybody in the world. Right now, if you want to, you can go to that service and access our very first quantum computer that we ever built that we called Aquila. And we have also taken these systems now and we've built them in a much more streamlined, engineered way, and we've even figured out how to ship them across the planet. One of our systems just shipped out this last year to the Japanese Institute of Standards called the ICE. And they're actually deploying it inside of a center that includes supercomputers and things like that they integrate inside of, and they become part of a computing stack that's really working on some of the world's hardest problems.
Yeah, and tell me about the AWS solution. What is that called again?
Yeah, so that's our first machine. Its name is Aquila, but we call it an analog Hamiltonian simulator. It was the first step that we made as a company to get our technology out into the world. It's on the earlier side of an analog to kind of digital divide. It doesn't work off of digital quantum gates, but actually is a more analog form of processor. So you can see just in that kind of 6 years that we've been a company and been able to commercialize this technology, we've already taken some key steps there. We went from analog to digital, and then we've gone from uh, error uncorrected digital to error corrected digital.
Hmm, that's wild. And you talk about a Hamiltonian, which is a pretty dense concept. A good friend of mine, a guy named Sean Brem, he's an expert in Hamiltonians and he knows all about how to do these things. It's a very, very dense concept. Can you give a sort of high level description of what that means and how you go about leveraging these things?
Yeah, so one of the things that that first machine was very good for was studying natural systems. So a lot of the terminology and the language that you hear has deep roots in the physics community that understands scientific problems like how to design materials and things like that.
Mm-hmm.
That word Hamiltonian really comes from how you describe a material at a very high level using mathematical concepts. And basically, the idea was that you could make programmable kind of virtual materials using that analog Hamiltonian simulator.
Hmm. That's crazy. And so this does get very deep into material science, right? That's why I think you said you're using rubidium. Is that right?
Yeah, yeah. So a lot of the applications are really inspired by things that are kind of on the scientific frontier. And one of the things that we do know that quantum computers probably will be very useful for is thinking about how materials work, particularly in the quantum limit.
Hmm.
It's a very natural application for a quantum computer, and that's the application class that we started with in particular because the people that understand those problems also happen to understand how a quantum computer is most likely to be successfully applied to a particular problem. So
Hmm.
we started from that, but have no fear. We believe that the impact of quantum computers will be very large. A very long time ago, Peter Shor taught us that problems like just factoring integers actually can be mapped very efficiently onto quantum computers as well. So
Hmm.
expect that, this is the first kind of starting point of application classes where we understand that they have scientific applications that are easy for the scientists to figure out how to use quantum computers to attack. But we expect over time that as the computers become better at what they do, and as people get better at understanding how to use quantum computers, we'll be able to apply them to a broader class of problems.
Hmm. Well, I think one way to describe it, and I mentioned this at the top of the call, that traditional program is linear in nature. Now, you do, of course, have parallel processing. If you look at the AI universe these days, GPUs really open the door to a lot of that stuff because they're very good at parallel processing. So you take this big chunk of data you want to analyze or process, and you divvy it up into lots of little tiny bits and spread it that way to get it done faster. But I think what quantum can do is look at problems in a much more multidimensional way, and that's why it can solve things faster. Is that a decent assessment?
Yeah, yeah, no, I think that's a great way of thinking about it. And actually, if you think you go back to the history of parallel processing, there was this idea that we needed to find the right problems to task parallel processors on, and there was this phrase, embarrassingly parallelizable, that fit onto the GPUs best. And people were looking for, what are the problems that actually match that criteria? I think actually one of the big questions about quantum computers today is what are the applications that are embarrassingly quantum?
Hmm.
And I think it's going to be kind of surprising what the answers are. Personally, I never would have guessed that factoring integers was in any way, intrinsically quantum or anything like that. But we've known for a long time that we can do that exponentially faster with a quantum computer. So
Hmm.
that gives me hope that there's actually many more problems out there like that. Now, I think we actually have to have the quantum computers in front of us and we have to start experimenting with them the same way that we did with classical computers to figure out what they're actually good for.
Hmm.
We have a few guesses right now, but the chances are pretty high that once we get to using them, we'll realize that there's a whole class of problems that are actually best done on quantum computers.
Hmm.
If you ask computer scientists how they think about classifying the difficulty of different problems, they have a very, codified way of going about that. Now we're starting to think about complexity classes of algorithms that might be sped up by quantum computers, and I'm really excited to find out what actually lies in that territory beyond what we already know.
Yeah, well, it makes a lot of sense. But again, so where do you think you are right now? Obviously, you've got some announcements now. You have some machines in production. You're sort of in the R&D phase. What's
Mhm.
the timeline, and is there a way to map this power to traditional programming artifacts? And I guess there is because you're on Amazon and that's connected. So like let's start there maybe. What are some of the some of the use cases people are generating or leveraging with what you have with Bracket?
Yeah, actually, so there are quite a lot of attempts already to think about different application sectors. So definitely thinking about biotech applications, designing molecules that could be drugs.
Hmm.
Uh, they finance applications, thinking about different types of optimization that might be helped with quantum computers. Certainly in chemistry, in industrial chemical processes, things like that. There are actually quite a few applications people have thought about. The most systematic attempt to really catalog all of the possibilities there was actually done by DARPA in the US in their quantum benchmarking program. They've actually surveyed a whole broad class of these different things and kind of ranked them against each other. And I think everybody wants to know, when is that first day going to come? The quantum computer has really done something that has, true intrinsic economic significance in the world. And since I have been working in this industry, which is embarrassingly long, I think everybody has said, oh, it's at least 10 years away. Um, I think, now is the first time that I've really heard a broad class of people, especially at our company, but I would also say outside our company at some of our competitors, saying we're starting to feel differently. We're starting to feel like we understand, how we can think of this as an engineering problem. I employ both scientists and engineers. The scientists like to say, oh, now it's just an engineering problem. The engineers throw their hands up and say, I mean, but maybe it's an ungodly hard engineering problem. But I think actually we can see daylight now. And we're starting to design systems that, probably are pretty close, a few generations away from something that potentially could show that economic significance. And we're actually able to put pen to paper, draw those designs out. And we may not have all the parts in hands to really do it yet, but we're starting to feel like that's pretty close. And,
Hmm.
key breakthroughs were really just being able to implement error correction in the laboratory and show that it works, and then start to think about how the applications really break down into algorithms that we can design using that error correction. And then how many resources do we really need? How many qubits do we need to implement that? How much time does a quantum computer have to run to do that? And then
Hmm.
really optimizing the design and the architecture of a quantum computer.
Yeah, this is really fascinating stuff. Well, folks, don't touch that dial. I'll be right back. You're listening to Inside Analysis. All right, folks, back here on Inside Analysis, talking to Nathan Gemelke. He's with QuEra Computing. They do quantum computing. They use atoms, neutral atoms, which I think is fascinating, in lasers, and they do error correction to make sure that it works properly and does what you want it to do. It holds the data. We were just watching Seinfeld last night in the famous episode where he rents the car, and the lady is like, "Oh, we don't have the car." He's like, "But I have a reservation." She goes, "Oh, I know what a reservation is." I don't think you do, because you have to hold the reservation, right? So you have to hold these atoms in place in order to get value from them. But as you're talking about the different applications, I'm thinking to myself, Bitcoin, apparently China is at the forefront of this, and they've built all these ASICs, these very focused devices that are designed just to solve mathematical problems. And what they're doing is mining for Bitcoin, just getting all the way to the bottom of stuff. What impact could quantum have on that use case? And is it possible that it could unwind these things so much faster? And you keep hearing all these fears about systems not being quantum proof, because if they can hack into your system, steal your money. Like, what's the downside? And can this stuff be used for Bitcoin?
No, I mean, all great questions. I mean, I don't think anybody should run off with their hair on fire. Cryptography has a long history in how it intersects with computing machines, and those two things are intertwined. And that game will go on forever. If there's something after quantum computers, I'm sure it will intersect with cryptography as well.
Right.
I don't think that you need to rush off and call your bank. I do think, though, it is important to start thinking about what people have called post-quantum cryptography.
Mm-hmm.
Does cryptography look in the era that we have quantum computers in the world? I think it's time to start thinking about that. There are concrete ways to plan ahead for that. There are algorithms that are thought to be quantum safe. Uh,
Mm-hmm.
kind of just stepping up a level and, like, looking at this from high altitude. The reason that cryptography and computing are so closely intertwined is that a lot of cryptography is built around a premise about what is hard to compute.
Mm-hmm.
And so if you look inside Bitcoin or you look inside a lot of the encryption systems that we use, there's an assumption made that a certain problem is very difficult to invert,
Mm-hmm.
in one direction, but it's very hard to run it in the other direction. And the problems that are hard in that way are pretty well understood with classical computers. So even if you were building, a special purpose ASIC to try to do those cryptography applications much more efficiently, there's certain things that we can say about classical computers and how many steps that they have to take in order to get an answer to a question that's hard to invert like that. Quantum computers potentially start to change which problems are hard like that. So, one of the things that you can do with a quantum computer that's pretty easy is compute its own dynamics. In fact, every quantum computer is at least good at one problem, which is understanding itself.
Hmm.
And in some ways, many of those dynamic problems are actually themselves, one-way functions that are hard to invert like that. So, one thing that you can immediately say is that, well, quantum computers should be the kind of thing that you can prove that you own one because there are functions like that you could show you have the answer to what it computes for itself. But also, you can start to worry that maybe the quantum computers change the rules about what is really hard to compute and what is a one-way function. And that's
Right.
definitely true. That's what Shor's algorithm has shown us about RSA encryption.
Hmm.
It's something to know about. I don't think that you are going to wake up one morning and suddenly all of the encryption on Earth has been broken. It's certainly going to take a lot of time and effort, even to use the world's best quantum computers as they come, into shape to be able to do this. It's not going to change the world with a bang. I think it's going to come on slowly. We like to focus on things that aren't going to break the world.
Yeah.
We
That's good.
are more concentrated on things like drug design and so forth with quantum computers.
Right.
And some of that stuff is probably more near term than the cryptography applications.
Right.
Definitely, any technology has to be brought into the world responsibly and in a controlled way. And understanding cryptography is an important part of that. We would like to see people use quantum computers and see how well they do at those sorts of tasks, but also use them to further cryptography and improve cryptography, which is the first step anytime a new computing technology comes out.
Interesting. That's a good point. Now I'm going to throw a curveball at you, but I'm guessing you know about this. There's a company we've had done some work with, very interesting, called That Dot, and they have a quine. A quine, of course, can represent and visualize its own running program as data inside itself. Are you familiar with this concept of a quine?
Oh, I'm very interested though.
Okay, so this is you're making me think about this because you talked about how quantum can be used to visualize its own system. And like a Hamiltonian is a sort of an algorithm to help you understand all the elements in the equation, if you will, right? You're really trying to understand all the forces at play, which of course is great stuff for meteorology, right? For predicting the weather, for doing all these sort of simulations and things. So it just got me thinking here to myself, this sounds similar to what we were learning about working with that dot and this fascinating concept of a quine. In other words, I'm reading just from ChatGPT. It can show its own internal operations, its code paths, ingest pipelines, queries, standing patterns, and transforms in real time as part of the live graph that it's building, right? Because you think about how the human brain works and why we're so good at solving certain problems that even computers have trouble solving now. And it's clearly because there is a graph in your brain that it is a truly multidimensional, I mean, with probably trillions of permutations graph that allows you to connect dots in your head and connect concepts and wrap things around and do all sorts of cool things. And this is you got me thinking about that in the context of what quantum might be able to help us do. But just with that broad sort of left turn I threw at you, what do you think about this, and what do you think about the possibility of quantum computing really helping us understand whole other disciplines and ways of computing and understanding things?
I think that what you're describing with classical computing systems is introspection, being able to
Hmm.
look at a processing system, being able to look at itself. Certainly with AI and so forth, that gets very meta very quickly. Obviously quantum computing isn't quite to that level yet. But I will say that if you think of quantum systems as things that could understand each other themselves, that's actually where quantum computing came from in the first place. You go
Hmm.
back very early days, the first time anybody brought up the idea of quantum computing, Richard Feynman gave a very famous lecture about this, and he said, when you go to simulate what small quantum systems do, in condensed matter physics problems, where you're trying to understand materials and things like that, we know that classical computers suck at that. That those problems are just hard to compute. So his premise of a quantum computer was use a quantum system to study quantum systems.
Hmm.
It's
Interesting.
compared to the classical counterpart, exponential better ability to do something like that. And so if you take that kind of, quantum systems as a whole and think about the introspection of quantum systems on each other, that definitely is kind of core to the whole idea of quantum computing and what we call quantum simulation. But I don't think that quantum computers are quite to the level of sophistication of classical computing systems.
Hmm.
That layering of kind of software constructs and so forth that you see in classical compute, it isn't as mature as to be able to provide that level of introspection. But you've got me thinking
Interesting.
about it a little bit now.
Hmm.
I really want to get back into the laboratory and think about things,
That's
maybe
good.
all part of a processor to understand the whole. That's definitely an interesting idea.
Well, because again, when you think about writing programs, and now we're of course at this very strange period. It's very exciting, but it's also a bit trepidatious, I suppose. Period in computing, where you have Anthropic with Claude, its ability to just spin up code in no time, where like all of a sudden the bottleneck is not the programmers. Because you think about information technology, the bottleneck has been the programmers now for pretty much the whole time. And all of a sudden, that's kind of a problem solved. And now the problem is almost more on the business side and the application side and the hardening and making sure things work in conjunction. Because one of the dangers with all this AI generated code is that yeah, it can do certain things, but in a major tech stack like that is running a bank, for example, you have to be very careful about what you unleash inside these environments because
Yeah.
it'll break things that you didn't even think about. And of course, getting back to quantum, maybe quantum can help us see all that, right? To see the graph, because you think about interdependencies, and that's what usually breaks things. When something isn't working, it's because there was some handoff that didn't work because either the system went down or there's too much traffic or whatever. There are all kinds of things that can go wrong. But what do you think about this fact that we're at this weird inflection point where now it's no longer the programmers that are holding things back? It's really the business people and the application design people. What do you think?
As a technical guy, I always want to blame the business guys for holding us.
I
Um,
can understand that.
if you go back, Eric, like 6 years ago when we started the company, it's hard to get your mind around this, but we didn't know at that time which would come first, a useful quantum computer or artificial intelligence. And I mean, it's amazing how much has happened in that time.
Yeah.
Now we're starting to get up to the cusp of useful quantum computing, but we definitely have useful artificial intelligence.
Hmm.
That has really affected how we think about not just the quantum computer as a tool that we're making, but how people will use it. I used to, really think hard about what is the future quantum computer programmer going to look like? And that is so hard to get your head around because quantum mechanics and quantum systems really don't behave in the way that the classical world around us does. And it's less intuitive to figure out how am I going to create an algorithm that actually works.
Hmm.
But for a long time we thought about how are we going to educate the people that come up with these algorithms. We had never really anticipated that it would be realistic to be talking about AI as running and designing quantum algorithms and taking a lot of the burden of making algorithms off of, a programmer.
Right.
And so now, our default context is actually most of the time we're thinking about how to build a quantum computer into an artificial intelligence setting. How do we get it to work in tandem and in concert with a high performance computer so that the high performance computer is using the quantum computer to do the intrinsically or embarrassingly quantum parts and then turning the results of that
Right.
into the useful information to solve the problem in the application that matters.
Right.
And that is just, it's truly amazing to watch all of these things kind of coming together. The people that design the AI systems are themselves, just fantastically creative and intelligent and intuitive people that are coming up with new solutions every day. And they're thinking about how to utilize a quantum coprocessor inside of, an HPC cluster that's running an AI application. It's really impressive what they've come up with so far. And, we've learned a lot about that.
Yeah, well, you bring up an excellent point, and I think this is where the real value is going to accrue is in figuring out where in a complex workflow the quantum engine does its job exceptionally well and can thus be leveraged on the other side, right? I figure all computers, what do? They take an input, they run some transformation, and they have an output, right? Like that's in a very, very simple sense, that's all they're doing. But now you figure, yes, we do have this Gen AI capability, which is amazing. It's hard to know how much it costs to be able to do that. I mean, there's been so much money dumped into these systems by these huge corporations. And, just even trying to figure out the amortization on the hardware is enough to blow your mind, right? So my point that I'm kind of what was it? Circumnavigating, I suppose, to a certain extent, is that there are ways to do things that are dramatically inefficient, and there are ways to do things that are amazingly efficient. And we have a bunch of stuff, I think, that is now being done in a very, very inefficient manner, which is very expensive and very
Yeah.
difficult and challenging and breaking budgets. And it's like there are other ways to do those things. And I think quantum is going to kind of open the door to being able to understand that and do a better job of architecting workflows and understanding the possible and understanding how to achieve the possible. What do you think?
Yeah, no, I mean, if you want a very clear example of something like that, when we go to design drugs, which are, in essence, are just mo small molecules,
Right.
part of that is just understanding the quantum mechanical system of the atoms in the molecule.
Interesting.
And if you can just get a lot of data about that quantum system, you can train an AI engine to try to fill in the gaps and extrapolate and guess about other molecules, how they work, and so forth.
Wow.
And so actually, when we use high performance computing systems to do that, one of the things that they're doing is just generating that data. It's much more efficient to use a quantum computer to generate data about quantum systems
Hmm.
than to use a high performance computer. But AI basically can ingest that data and train itself on that data and then start to kind of make guesses and fill in the gaps and so forth the way that a person might intuitively do that. And now that means that, all that data that we might have had to get either through very aggressive numerical calculations on supercomputers, or, dear God help us, we have to go to a laboratory and actually make some measurements of things.
Right.
That's expensive to do, but running a quantum computer actually now we can see where that economic advantage comes from because we get literally, some dollars per data.
Wow. This is just wild. And it does take a group effort. You have to be talking to all the other researchers, figure out what they're doing, and kind of figure out how you fit into that mix. But folks, don't touch that. I'll be right back. We're talking quantum here on Inside Analysis. All right, folks, back here on Inside Analysis, talking to Nathan Gemelke. That's Gemelke. He is with QuEra Computing. They're doing amazing things with quantum. And Nathan, I wanted to get into the optics again. In other words, the lasers and these rubidium atoms, these neutral atoms, and how you're able to isolate them because you're cooling them down with lasers, right? And
Mhm.
then I guess if I understand it correctly, you're able to keep them in in a position. And you talked about the decoherence. You want to avoid that, so you have to
Mhm.
keep the system very stable to keep those guys in place. But then what you're able to do is have many of them, and because you can have zero, one, or the superposition, you have many more possibilities, which means you can store lots and lots and lots more data, which then again has to be accessed. So, like, maybe let's focus on the persistence side and then the access side. When it persists, what is it doing? You're just getting it into a position, and then when you access it, you're reading the position. Is that right?
Yeah, yeah. So, basically the basic element of information is the state that the atom is in. And,
Mm-hmm.
literally for an atom, you've got, a nucleus and you've got a bunch of electrons. And in that atom that you mentioned that we use, rubidium, there's one kind of loosely bound electron. And that's the only one that we really touch. And what we do is we do one of two things. We either flip its spin state or we excite it into a very highly excited state. And when we do that latter one, what that's called is exciting it into what we call a Rydberg state, but it's like the 1950s cartoon of an atom at that point.
Hmm.
Electron is so far away from the nucleus that it's actually orbiting in this giant circle.
Hmm.
Does that, if you have two of them that are in that state, they interact with each other, even if they're pretty far apart. So that's actually, that's the secret sauce to, how we actually entangle atoms together is we get them to interact while we're putting that information in.
Wow.
So, that entanglement is a really kind of unique thing where, if you go to look at the state of one of the atoms, the electrons in one of the atoms, you can actually have a back effect on the other one, you know.
Hmm.
So that's the spooky kind of quantum mechanics effects that you have when you actually start to look at the state of the system.
Right.
All the information is really, it's caught up, it's encoded in those manipulations of the electronic state of the atoms and the entanglement of different atoms with each other. And then how well you can preserve that as you make a bigger and bigger processor that might have thousands, or at some point, maybe even millions of atoms in a single processor like that.
Hmm. That is just absolutely wild. I keep trying to think of different ways to describe quantum states to people, things like superposition, things like entanglement. And I came up with an example. It might be a bit far flung, but I'm curious to hear your thoughts on this. I was trying to come up with some metaphor to help describe what this could mean in the real world. And what I thought of is the stock market, like your stock portfolio. So you have like I don't have many stocks, but my dad's big in the stock market, so he has a lot of different stocks, and it's a fluid environment. Now you can look at the value at any given point in time, but it's not really the value until you sell something and then there's a trade executed, and at that point in time, now things have changed. But until then, it was like a superposition because anything is possible. But
Mhm.
when you make that transaction, that's like when you look at something and by looking at it, you change its state in quantum. What do you think about that?
No, it's not a bad analogy. I mean, there are classical forms of correlation that are pretty different from what quantum mechanical systems do. So if you only own two socks, one is red and one is blue, and you see that on your left foot you have a red sock, uh,
Mm-hmm.
that you have a blue sock on your right foot.
Right.
No correlation. There's
That's
no
funny.
quantum mechanics there, and unfortunately, otherwise it'd be a lot easier to do what we do. Uh, but I mean, it's definitely true that when you go to observe a quantum system, you are doing what's called collapsing the state of that system, and that measurement has a kind of back action on the whole system at large. And you can use that really to help yourself, but it can also hurt you too, right? So if you are looking at a system and you're extracting information in a useful way, doing things like error correction and so forth, that's a good back effect. But unfortunately, you're not the only one looking, right? So actually, the whole world is looking at your quantum system, and this is part of the reason that we call it decoherence. As the rest of the world is kind of looking at what that quantum system is doing, it's also kind of collapsing that wave function and making it a more and more classical system.
Hmm.
Actually, if you study quantum mechanics as a physicist, you open up that textbook on day one of class one, when you show up at the university. One of the first things that you read in that textbook is that as a quantum system gets bigger and bigger, that effect of the environment around it kind of interacting with it will make it more and more classical.
Hmm.
If you look at what people that are building quantum computers are doing, it's really actually trying to change that first page in that first textbook of quantum mechanics and produce systems that are so well controlled and so well isolated from their environment that they're containing their information and keeping it in that precious quantum mechanical superposed and entangled state
Hmm.
in a controlled way and being able to utilize that to explore how information can be represented and processed and move between states in a way that is different from classical mechanics and more efficient at getting to certain answers.
Hmm. Wow. That's fascinating. So, are you guys hiring? For anyone listening
Well,
who's like, I
Eric,
want to get into quantum.
you're doing pretty well here, so I'm thinking about it. I got to see what socks you're wearing before I can really commit.
Oh, that's right. I don't have my own red and blue socks on today. But I think this is very fascinating, and I think that what we need here in the world of AI, because again, there's just all this investment into generative AI, and it is amazing. There's no doubt, but it does have deep fundamental flaws in how it does things. It generates stuff, and so there's all this effort being put into retrieval augmented generation and fine tuning and guardrails and all this stuff. And actually, I'll close with this and just see what you think about it. I think it's fascinating that over the past 50, really 75 years, we've been working on information systems and really focused on the database and making it faster, more performance, more concurrent users, more connections, all the apps, all these things. But the point is that in the database world, and that has been the foundation, one thing was never in question, and that was quality, meaning you would get out of it what you put into it, period, no questions asked. Now with this Gen AI stuff, it's a different storyline because you're generating stuff. And so it's almost like we put a big noise filter on the end of this pristine 75-year process. It's like, well, why would you do that? And the short answer is because it does certain things so incredibly well. You can now talk to your computer in normal language. Not that you couldn't before, NLP is not new, but it's just so widespread now. But what do you think about that inflection point and how it could possibly dovetail with quantum?
I'm hopeful that there's a lot there. I mean, I think, it's one step at a time. And right now, I think we would like to see that we can do the, basic fundamental steps of making quantum algorithms really work, show things like Shor's algorithm actually functions in the real world, figure
Right.
how to get that to happen. But after that we've shown that, I do think that there is a really fascinating question about how these new ways of thinking about programming and information processing that are enabled by AI really get turbocharged by quantum solutions.
Hmm.
What's unique there is just that, there are certain problems and certain ways of connecting the dots that classical computers are just really bad at, and that includes AI. And suddenly, when you change the rules of the game, and there's a coprocessor in there that's good at some of the things that the classical machine is bad at,
Right.
it's amazing what answers I think we're going to be able to find. And I would posit that the human brain is a classical processor of its own.
Right.
And so the limitations of AI and of natural intelligence of humans may be limited by the same things. And quantum
Right.
computers may have access to certain answers that we just have never really had access to before.
See, that's very interesting. We'll have to follow up with you and get you on a future show, and I'll bring in some of my other pals. There's a guy, a good friend of mine here in Pittsburgh. He works for a company called Optima. Lou Simon is his name. He's very, very forward looking on the AI stuff, and he had a way of describing what the Gen AI does these days that really blew my mind. He goes, "Look, it's an intelligence." He said, "If I walk into your office and you ask me a couple questions and I just tell you something." Is it absolutely positively true that I'm correct? Probably not. I mean, sometimes we're wrong about stuff, but we learn from the intelligence and we get better at things. And it was a very interesting point because, again, back to my point about classical computing and databases and accuracy and deterministic outcomes and so forth. That's all true. That's what we want. We want systems that do what they're supposed to do every time and get the same output. But in the discovery side, the intelligence side, that's a much different story. And
Yeah.
so you just have to learn how to take what these things say with a grain of salt. Anyway, final thoughts from you. 30 seconds.
I think personally, I am often wrong. I
It's
think the
funny.
world at large is often wrong. And one of the things that we're likely to discover is that the best uses of quantum computers we haven't thought of yet.
Wow.
So that the humility to go out there and use them to discover, I think, that's the next hurrah. That's the next big phase of quantum computing, is just to put the pride aside, start
Hmm.
using these things and just see what they're good at and
Wow.
fun with it and see what we learn.
That's awesome. Well, folks, look this gentleman up online, Nathan Gemelke from QuEra, QuEra Computing. We'll talk to you next time. You've been listening to Inside Analysis.